None of that's memorialized.
And did you get a chance to look at the paper?
One you sent me yesterday?
Yeah.
Give me yesterday. No, I didn't. Actually, I don't even remember where I've kept it right now.
I'll email it to you.
Okay, well, one of my students had forwarded it to me last week.
Oh, they did, okay.
So, then this past week hasn't been my best week for reading stuff.
So we're trying to use that for, we'll see how it goes.
Snake. Snake.
Yeah.
Snake baby.
I mean, by their account, it's supposed to be like faster and be able to train on longer sequences.
That's the key thing, is like, it's supposed to be great for like long-term sequencing. Right, and linear, with the, linear scaling, so.
Yeah, I must. Where did I keep the paper down at? Can you send me a PDF? Yeah. Because I have a student working on exactly the same problem. And so my solution was to make it recurrent. So you can do the attention model. You can combine attention and recurrence.
You know, I was thinking about that same thing, actually.
Yeah.
Like, just like a dictionary lookup sort of thing?
No. So you can have it do it in blocks, but then each block could spit out a summary, right, which the next block could use in addition to everything else. And so if you could do an effective summary, then that summary effectively carries your state. Mm-hmm. So this actually gives you a way of not only having essentially linear time recurrence, right, scaling, but also of carrying your context around with you. Right, you could plug it into any model, and this is my context. Mm-hmm. Continue, right? Yeah. It's bhiksha@cmu.edu, bhik@cmu.edu. Yeah. All right, guys. Stay blessed. Okay, all 5 of you. Your name tags out because, obviously I don't know your names by now, but still. 7 of you, sorry. My apologies. And let's begin. The attendance poll is 938. My TAs are absent, which is lovely. Okay, let's begin, guys. Thank you for coming in on this very rainy and very cheerful morning. We're going to change topics. We've covered the basics. What we've covered so far, we've looked at briefly at the history of neural networks, explained how it's a universal approximator that can basically model any function at all. If the parameters of the architecture and parameters are appropriately chosen. Then we spoke of MLPs. We spoke of how we can train these MLPs to model any particular function. Then we also showed how you could scan for patterns for position invariant pattern detection and how this gave us a convolutional neural network. Morning, Mia. So, and we looked into training convolutional neural networks and a few variations on the theme. Now, we're now switching to a different topic. We're going to be talking about recurrence, how we model time series. So in many situations, we must consider a series of inputs to produce an output, where the outputs might also be a series. For example, say a speech recognition problem. Now, you have an entire recording, and at the end of the recording, you have to figure out what was said. So this is where you cannot actually determine what was said till you have analyzed the entire sequence of recordings. Now, here you have a time series data, and the actual inference requires analysis of the entire time series, or something like this, which is an annual phenomenon, because our wonderful Pittsburgh Steelers are really bad. But anyway, the Steelers, meanwhile, continue to struggle to make stops on defense. They've allowed on average 30 points a game and have shown no signs of improving anytime soon. Is there anything over here that tells you what game is being played? Is this a positive sentiment or a negative sentiment?
It's a negative sentiment of the football team.
So the point is, in order to have an idea of what game could have been played, they're allowing 30 points a game. That doesn't sound like basketball. It's too few. Doesn't sound like baseball. It's too many, unless the Pittsburgh Pirates. And then, so this must be football, right? But then you have to get all the way to the end before you actually can make an inference. Or the stock market. You have to look at the entire sequence of stock values to decide whether something is worth investing in today or not, whether you must buy a stock or whether you must buy an option. So this decision must be taken considering how things have fared over time. All of these are classification and prediction problems where you are considering a sequence of inputs, and you produce one or more outputs. And this can be done, obviously, like every other prediction and classification problem, using neural networks, because as we know, neural networks are universal approximators. Now, before I continue, I'd like to actually clarify some of the illustrations that will follow in the classes that, in the next 7 classes, next series of lectures. Typically, we've been drawing neural networks in this manner, where you have a vector of inputs, and then within each layer, you have a collection of neurons, which compute their outputs based on the output which receive as inputs the output of the previous layer. And so we've explicitly illustrated all of the neurons in each layer and all of the components in the input. Now I'm going to rotate the picture on its side. So this figure is now going to look like this. So every time you see one of these squares, you must imagine that it's actually an entire vector of inputs going into the page, and that it's fully connected to whatever comes just below it. So this network, for example, would be shown by this vertical diagram. If it had something like this, then the figure to the left, the figure to the left is going to be shown as the figure to the right, and the same thing over here, right? So the illustration makes sense. So when I draw something of this kind, each box actually represents an entire vector of inputs going into the page, or vector of neurons going into the page. So let's go back to our problem. We want to make a stock prediction. And in order to make a prediction for whether a particular stock is worth investing today or not, you really have to consider all of the stock values in the past. And how would we do it, right? Now, at the least, to get an idea of the trends, you have to look at the stock values today and the past several days to decide if something is good or something is going the right way or not. And so you'd have a network of this kind, where to make the prediction on any given day, you're going to look at the stock values on that day and the days immediately preceding. And this is what you would do on each day. So on every single day, you're going to look at the stock values on that day and the days preceding. So what kind of network is this? something that just slides over the input. That's just a standard convolutional neural network, right? This is a time delay neural network. So this is good, but then this has a limitation. And what is the limitation over here? That it's a finite response system, meaning something that happens today is only going to influence predictions for the next few days. And beyond that, it cannot influence predictions. So if you had a window with n that you were looking at, then the prediction at any time t is going to be dependent only on the inputs at time t all the way through t minus n. And anything beyond that is going to be ignored. So if an event happened at the time shown by the red box, then the first time it's going to influence a prediction is when you're making predictions on that day. It will continue to influence predictions for a few days. And in the particular example that I have, after only 4 days, the events that happen on the day shown by the red box are no longer going to be influencing predictions. And this, of course, is not a great way of making stock predictions. You really want to look at longer trends. So to make we have the situation where if you want to consider more of the context, you need to consider more of the history. And if you were following this architectural format, then you would actually just do that, right? You could just increase the number of time instants that you're considering on any given day. But then this is not quite going to cut it. Sure, it's going to take more CPU. It's going to take more memory. But that's something that we can afford. The real issue is this, that if you're considering something like the stock market has daily trends. To figure out what's going to happen today, you want to look at the past few days. But then you have other kinds of trends. You have weekly trends. Now, Mondays are when you have more activity than you have on Fridays. Typically, if you're tracking any stock, you're going to see the stock value shoot up on Monday. You're going to see it. And if they're going to dump it in the market, they typically do it on a Friday, just so that you can stew over the weekend. Similarly, you're going to have monthly trends. Anytime people get their paycheck, they're going to go and do some stuff in the market that's going to influence stocks. You have seasonal trends. You have purchases and stuff happening at the end of every season. Or you have annual trends. Every Thanksgiving, things go up. And what is going to happen on this Thanksgiving is kind of predictive of what might happen at next Thanksgiving as well. These trends carry over. Although the further back in time you go, the relevance of events way back when fades over time. So if we want to capture this kind of history, you effectively want to be looking at all infinite history. But then if you want to look at all infinite history using the convolutional format, you're going to run out of time, memory, and parameters. This just doesn't make sense. But then here's a different way of doing it, right? But before that, here's the first poll. Okay, anyone want to take the first question? Yes. True. Second? False. Thank you. Right. So convolutional neural networks are finite response systems. They're only going to affect the input to output for a finite duration of time in this case. And so the second one is obviously false, right? What we want is an infinite response system. We want something that happens today to have some bearing on predictions for the rest of time. And how could we do such? How could we design a system of that kind? One simple way of doing it is to simply have the predictions of today influence the predictions of tomorrow. So the network could just take in the prediction at time t minus 1, yt minus 1, when it wants to make the prediction at time t. Now, so what would happen here? If you have some input x0 at time 0 and no further inputs, x0 is going to cause a prediction, y0. But then at the next time, although there's no input x, you do have y0. And so y0 is going to influence the prediction at y1, which is going to influence the prediction at y2, and so on. And so a single input is going to influence outputs for the rest of time. This is what is called a NARX network, or a nonlinear autoregressive network with exogenous inputs. So it's autoregressive because its predictions are based on its own past predictions. It's regressing on its own predictions. And the output, so here we are indeed considering the entirety of the past. How so? Look at what's happening here. Let's say I have some input at the initial time instant. It's going to affect the prediction of the current time. That prediction goes in as input at the next time. And so that's going to influence the prediction at the next time. And the prediction at the next time is going to influence the prediction at the subsequent time instant, and so on. And so what we find is that an input at any time can, through this chain, influence predictions for the rest of time. The system now has memory. It has memory about everything that has happened in the past. But where is the memory stored? In which variable is it stored? It's stored in y. The memory is stored in the output, right? So if I were to draw this entire sequence of inferences, this is how it looks. An input here is going to influence the output here, which is going to influence the output here, and so on. And so long as you have an arrow between any input and any output, you know that is influencing the output. And as you can see, every single input, no matter how far back it has occurred in time, is going to influence the current output. So this one has infinite memory. It's an infinite memory model. I'm just going to simplify this picture. In this picture, I'm actually showing a yellow box for the output variable. But the way, a cleaner way of visualizing it is that whatever comes out of the output layer at the current time goes back in as the input at the next time, right? And once again, you can see that an input at time t equals 0 influences predictions forever. Now, you're not restricted to looking only at the current input and the immediately past output. You could be looking at the past several outputs. You could be looking at the current and past several inputs. So the generic NARX network has a structure of this kind. But what remains is that the memory of the past is embedded in the outputs. There's no variable within the network itself which explicitly tries to contain the memory of the past.
Why not so many green boxes? Is that necessary for this? Or?
In this case, no, I just have two hidden variables, two hidden layers, right? It's just a picture. Now, NARX networks are very popular for time series predictions. They still use them, where you just feed the output back in as the input. Again, it's an autoregressive network, and in fact, we still use NARX, the autoregressive structure, quite a lot. Now, they had gone somewhat out of fashion for a while, but then when LLMs came in, all of our predictions are autoregressive. The prediction that you make now is going to determine the prediction that you make next. So when you're generating a sequence of words, the current word influences the next word. But initially, they were used to predict stock markets, and they were used in any kind of problem where you had to track things, and of course in language. Now, the key bit here is that there's no variable within the network itself that stores memory. The memory is stored in an external variable, namely the output. Now, what if we want to move the memory into the network? That's more of an explicit encapsulation of the memory into the network itself. So now the architecture of the network explicitly considers the fact that the input is a time series, whereas in the NARX structure that we saw earlier, there's nothing in the network structure that told you that it was specialized for a time series model. So in this kind of setup, we want to have a memory variable of some kind, which I've represented as M, which is part of the network, which captures or stores the memory of the past. So you would have a memory variable of some kind, which could depend on past values of the memory variables, past hidden states, past outputs, and inputs. And the hidden states themselves are now going to be functions of both the current input and the memory, and the output of the network depends on the hidden states. This was how memory was incorporated into neural networks in the early models. And I think the first person to actually come up with a model that explicitly captured memory was Michael for his PhD thesis, I think. These were called Jordan networks, where you included a specific memory unit shown by this blue box. And this was part of the network which retained everything that was called memory. But there was nothing special about this. All that he did in this particular case was to have a running average of current and past outputs. And so the so-called memory variable just stored some alpha times the current output plus 1 minus alpha times the past memory. In other words, you're still using just the outputs as a memory. The fact that you've got a specific variable which maintains a running average of outputs has not really changed the fact that the memory is still external to the network. And so when you train this network, you still train the network just as you would train an MLP, where you could chop it up into individual columns, where one of the inputs at each column was the running average of the memory. So this guy, Ellman, came up with an improvement on this model, where for the first time, he actually introduced a variable within the network itself to store memory. He called this the memory neuron over here, was it? I don't quite remember. But this was the so-called context state, also shown in blue, which carried memory. But then the way the context state worked was that it was an exact copy of the hidden state at the previous instant. So instead of remembering the output at the previous instant for memory, you remembered the hidden state. Now, this network was called a partially recurrent network because when you wanted to train the network, the way you did it was to basically chop this up into columns. And so this portion was one column. This was a second column. And you treat each column of this picture as a separate training instance and use this collection of columns to perform gradient descent in and update your model parameters. Now, what that means is that gradients didn't go across time. So gradients only moved downwards within each column, but didn't actually flow across time to previous times. So this was called a partially recurrent network. And well, in many problems, the influence of any particular input may not be immediate. It could occur several time steps down. Something that happens this Monday could only show up in your outputs next Monday, right? And this model doesn't capture that kind of phenomenon in its training. Yeah.
When you say that the gradients only go downwards for the memory states, does that mean that each of those blue boxes do not have shared parameters?
They're all shared parameters. It's just this. So let me draw the figure. I have, this is my input, and this is my output. Now this is cloned. And so these two are the same. And then, right? And then at the next input, you have some other output. And so now when you train it, you basically erase these connections and now treat this box and this box over here as separate training instances in a batch. So now, if you have any error over here, the derivatives can move here, they can move here, but then there's no flow of derivatives across time. Right? So this fails to account for the fact that events can have their influence way down in time. And in order to actually be able to capture this, you want those gradients to flow all the way back to the gradients of errors to flow all the way back to whatever triggered them. And that isn't captured. So these were what were called partially recurrent networks. And so the story so far is that in time series analysis, models must look at past inputs along with current input. And simply looking at a finite horizon of past inputs gives us a convolutional network. These have short memory. So if you want to look into the infinite past, you want recursion. NARX networks recurs by feeding back the outputs to the input. And these may feed back even a finite horizon of, yeah.
When there are many layers in the hidden layers, will the memories capture, state storage or the state of the multiple layers?
Pretty much. So you can think of the collection of hidden layers as one hidden block, right? So you may even feed back a finite horizon of outputs. And we also saw a couple of model architectures where we tried to have some component of the network itself explicitly store memory. These were what we call the simple recurrent networks. The Jordan networks maintain a running average of outputs in a memory unit. And L1 networks store hidden unit values instead of the output for one time instant in a context unit. And these are simple or partially recurrent because during training, there is no flow of gradients across time. So the flow of derivatives is blocked at the memory units. There's a second part. Okay, anyone want to answer the first question? Kyle, first question? False?
False.
And the second one? True, right, okay. And so memory neurons have true recurrence? They do not. Because while they do carry information across time going forward, during the process of training, the gradients do not flow backwards. And memory neuron networks actually dedicate neurons specifically to store memory. So now you do have an internal network component that's useful for memory, right? Now, yeah.
How is this different from residual network?
So what happens in a ResNet? Firstly, the ResNet is not across time, right? Second, it's called a residual network because you're computing residues. Residues are corrections, and you're always adding things back. So the input is added back, or whatever is computed from the input is added back to the input. That's why it's called a residue network or residual network, and that it's always learning residues. It's not transforming the entire input, right?
What is the main distinction in time step?
Here, these could be residual structures. These are two orthogonal things, right? So here, the idea behind a residual network is this. Whatever process, and this gets summed back. Whereas the idea behind recurrence is that there's stuff going across time. Right? Anyway. So here's an alternate way of looking at this, at things. We can actually, instead of feeding the output of the network back in, you could feed the hidden state of the network back in. Now, when you looked at the Elman network, the Elman network did this strange thing. You computed a hidden state, and then you cloned it, and then fed it back to the hidden state at the next time. Now, instead of cloning it, why not just do this directly? You know, it's an obvious next step, right? And now in this case, if you did this, now you can actually have the derivatives flow backwards across this connection as well. And that gives us this model where you have, it's a state space model. There's a hidden state H, where the hidden state value at any time is a function of the hidden state at the previous time and the current input. So ht is a function of ht minus 1 and xt, and the current output yt is a function of the current hidden state. Any of you who's worked on control systems recognizes this model immediately, right? So ht summarizes the state of the network. It carries information about the entire past. And the predictions made at any time simply depend on the state of the network. Now, for this to work, of course, at the very first time instant, at time 0, you will also need hf minus 1. And so the initial value of this hidden state must be specified. And once we do so, that's part of the model specification. You have what is called a fully recurrent network, or simply a recurrent neural network. So here's what the state space model looks like. The basic unit looks like the figure on the top. At any time t, the hidden state is computed from the current input and the hidden state at the previous time, and the output is predicted using the current hidden state. And the overall computation looks like this. At time 0, you have this hf minus 1, which is a model parameter. You take the current input, the hidden state value is computed using the previous hidden state value, and the output is computed from the hidden state. And then at every subsequent time, the hidden state at that time is computed using the hidden state at the previous time and the current input. And the hidden state is used to compute the output. So now look at this. Because of this recurrence in the hidden state, recurrence meaning it's always computing its current value based on the immediately past value. If I have an input at time 0 and no further inputs, the input at time 0 is going to influence the hidden state here. But then that hidden state is going to influence hidden states all the way through time, and then it's going to eventually influence the current output. So if all you had was a single input at time 0 and no further inputs, you're still going to have a sequence of outputs which all depend on the input at time 0. So an input at any time influences the output forever, which is basically the kind of characteristic we were looking for. Now, I've just represented the hidden state, yeah.
When the hidden states are being transferred across time like this, can we assume that in backprop the gradients are also being?
There will be, yes, right? And so now here's what it looks like. I've just shown in these figures, I showed a single green box for the hidden state. Doesn't have to be a simple thing at all, right? It could be that hidden state can be arbitrarily complex. It could have many layers. And whatever the structure of the hidden state, the entire structure of the hidden state must also be specified at time -1, the initial value. And so if my hidden state consisted of just a single hidden layer, this is what your network is going to look like. On the other hand, if my hidden state had 2 layers just sequentially connected, this is what your network was going to look like. You can even have uglier connections, like connections of this kind or something of this kind, right? All of these fall under the general framework of recurrent neural networks. The key point is that the hidden state, what I'm calling the hidden state, can be an entire complex module with all kinds of connectivity. The key characteristic is that these values are computed based on their past values, their values at the previous time. So that's what gives us this behavior that an input at time 0 affects the output for all time. And now, once you figure that you can actually have infinite influence, or you can be influenced by the infinite past using a recurrence of 1 step, there's nothing stopping you from having deeper recurrences. So for example, you could have a network of this kind, right? Where the hidden state at any time is computed based on not just the hidden state at the previous time, but also the hidden state two time steps prior. And to make this work, all you have to do is to ensure that these hidden state values are all specified for time 0. So the initialization of the network will also require HF -2 in this case, right? And again, this is a recurrent network. Although I've shown it as one unrolled network, what you must remember is that every column is identical to every other column. Basically, each column is performing exactly the same computation as every other column, meaning they have the same parameters. The only thing that has changed are the inputs and whatever came in from the past. Now, in real, yeah.
So if like the weights are the same between, like the weights of the connections between memory units are all the same, then how would you model something that's like the Monday to Monday effect? You talked about previously if the weight between everything is the same.
So the idea here is that we'll actually get to that in a lecture or two. But if these weights are properly learned, then the theory is that something that happens this Monday is going to fade slowly enough that by next Monday you're still going to have some influence. Yeah.
Then I was wondering how it handles like data sparsity. If each column has to be identical, like what happens if at time step 1 you're missing one of the values, but it shows up at time step 2 and 3, you're missing it at 4. Like what if the data inputs are different at each one of the time steps?
So you're really speaking of missing data, yeah. Right? Think of that as dropout, right?
Okay.
That's about it. So, okay. Now, when you actually look at the older textbooks on neural networks, they like to represent recurrent neural networks using figures of this kind. And when I first saw these figures, I was very confused. Why is the output going back in? The output is not going back in. Those loopy connections, they simply imply recurrence. And again, remember, each square represents an entire array of values going into the page. And so a figure of this kind actually represents the recurrence shown in the figure below, right? Or something of this kind means that I have a hidden state which has, I have 2 hidden states, and each of them are recurring on themselves, meaning the hidden state value at any time, each of these green boxes is computing its value based on whatever is coming in from below it, but also its own value at the previous time step. Yes,
Each of these columns scanning like a convolution, are they looking at the entire input?
This is not a convolution at all, right? So this is what it's going to look like. The actual computation is going to look like this. So what this means is that, what this figure means is that at each time, this is the computation being performed, except that the hidden state value is also considering as input its own value at the previous time step, right? And this figure, for instance, means that at any time, the first hidden state is being computed based on the current input and its own value at the previous time. And the second hidden state is being computed from the output of the first hidden state and its own value at the previous time. That's it.
So can we think of time as like epoch?
Not really, right? If you thought of time as an epoch, then you're thinking of each column as an individual independent element, whereas you have gradients flowing backwards.
Okay.
Right. For the element network, yes, you can think of times as epochs, right, or iterations. Or here's a more roughly recurrent neural network. Again, the point is, how do these figures translate to actual computations, right? Now, how is the actual recurrent computation performed? If I have this network over here, where the hidden state has just one layer, and it's computing its value based on the current input and the hidden state value in the past, there are different sets of weights. Now, having this recurrence gives us two distinct types of weights. One are what I call the current weights, which are weights corresponding to the vertical arrows. And the second is what I call recurrent weights, which are weights corresponding to the loopy arrows. And so if I look at this first hidden state here, that is, in order to compute that hidden state, first you compute an affine function of the input and the hidden state at the previous time. So this term within the parenthesis is going to be a weighted sum of the inputs plus the weighted sum of the hidden state at the previous time plus a bias. And this is what is going to be operated on by some activation to compute the hidden value h. The output y, of course, is simply computed on an affine function of h. And so you'd compute a weighted sum of the components of h plus the bias. And then you'd operate with an activation function on that to compute your final output. And typically for hidden states, for reasons that we will get to in the next class, the activation function uses a tanh. So the overall computation in vector format would look something like this. For the first hidden state, you're going to compute a weighted sum of the input using what I will call the current weights shown by the superscript 1, which means that these are the weights going up from the bottom, plus a weighted sum of the hidden state values at the previous time. So that's shown by the second term. The hidden state at the previous time is multiplied by W superscript 1, 1. Now the superscript indicates that with the two indices indicates that it's a recurrent weight connecting layer 1 at the previous time to layer 1 at the current time. Plus, of course, the bias because it's affine, right? And this affine term is then operated on by an activation function. So you have a current weight and a recurrent weight over here, two different sets of weights. And for the output, of course, this is just a standard computation. We're computing some affine function of the hidden state value itself, which is h times some weight w plus a bias, and then you have an activation operating on it. Right? Is the computation clear over here? Now, if my hidden state had two layers, the connection, the computation is going to look much the same. So in the first layer, this one, at any time t, you first compute a weighted sum of the input and the hidden state at the previous time. So this weight is the recurrent weight. And that affine term is now operated on by the activation function for the first hidden layer. For the second hidden layer, again, it'd be computing an affine function of the output of this guy through this current weight and its own value at the previous time through the recurrent weight associated with that horizontal arrow, which I've represented as W superscript 2, 2. And then you'd have some activation operating on that affine value. And so you see how this works. At each of these hidden states, you have current weights, which correspond to vertical connections, and recurrent weights, which correspond to connections from previous times. So you have two different sets of values. And then once again, the thing to remember is that every column is identical. Basically, you're performing the same computation at each time. Nonetheless, you can think of the entire picture as one large neural network where all the columns share parameters. So it's also simultaneously also a shared parameter network. And so here are computations for this uglier network, right? Now, once we sort of agree that this is the kind of computation we can perform, then we can see that there are all kinds of variants on this basic theme. So you could have so the first figure shows a conventional MLP. The hidden state is computed from the input, and the output is computed from the hidden states. Straightforward. But then you could have operations of this kind, where you have a single input and a sequence of outputs. Can you give me an example of something of this kind? Where would this work? Or where would you see a structure of this kind?
Generate an image based on. Oh.
Pardon me?
Generate an image based on.
Generate an image. Yeah, an image is not really a time series, right? But yeah, the input could be an image, and I could be capturing it. So that one blue patch going in could be an image or features from an image, and the output sequence could be a sequence of words. So this would be a captioning problem, right?
Or it can be
Or it could be
a series of words.
that would be this model over here. The second model is where you take an entire sequence of inputs and then produce a single output. That would be something, for instance, that you'd perform, for instance, when you are performing sentiment analysis. You read that entire sequence of words for the describing the Steelers' latest game, and it's not until you get to the end that you determine that this was a loss and not a victory, right? But which is default. Or you could have something of this kind, where you look at the entire sequence of inputs, and only when the entire sequence of inputs has been processed do you begin generating the output. So can you give me an example of where this would be relevant? Generating?
Generating video from text.
Video from text.
Time series forecasting.
Machine translation, English goes in, French comes out, right? You'd have to look at the entire English text before generating the French text. So you'd have to process the entire input before you process the output. And the kind of models that we've been looking at are the ones to the right, where at each time you're making a prediction. Now, believe it or not, the model to the very right, the bottom right, or in this case to the right, that's the most generic model. The other models that we saw are basically extensions of this model where you're ignoring some inputs, some outputs, or you don't have some inputs. So we will actually analyze this model, and we will begin talking about the other models later when we get to specific problems. Now, all of these are state space models. And so a story so far, adding to what we saw earlier, is that state space models retain information about the past through recurrent hidden states. These are so-called fully recurrent networks. The initial value of the state at time 0 is now an added parameter of the network, which may also have to be learned. Although more often than not, we just initialize them to 0. And state space models have this ability to actually allow the current error to influence derivatives way back when. And so to propagate error gradients across time. Questions? Is there anybody on Zoom?
Lisa is on Zoom.
Okay, any questions on Zoom? No, okay. All right, so how do we train this network? Now, this is just a giant MLP with many shared parameters. And so training the network is like training an MLP, but there's one key difference. And the difference lies in the fact that you're generating an output at every time. So if I took this entire network and flipped it over on the side, it's going to look like a standard MLP diagram that we've been drawing. Except that you'd be seeing outputs coming out from what looks like layers. So here, again, just as we perform back propagation in regular models, where do we begin back propagating from in a conventional MLP? We start at the top, right, at the output. So we're going to start after the final computation has been done, and then you're going to propagate the error backwards. Yeah.
I'm sorry to go back a little bit. What does the memory block look like? It just looks like a normal layer of neurons.
The memory block, that's just a hidden state. It's just standard, right? Nothing unusual about it at all. This is just an MLP, except now it's going to be getting inputs from the previous time instant, right? So here, when we perform back propagation, we always have to start off with the final computation and pass the derivatives backward. Here, the final computation is going to be at the final time instant. And so the derivatives would start from here and then go back through time. And so because you're going to be passing derivatives backwards through time, we call this back propagation through time, BPTT. But for the rest of it, training is as you would imagine it would be, except that you now have to consider that everything is a time series. So your training data are going to consist of time series, sequences of inputs, and the corresponding sequences of desired outputs, because you have a desired output at every time. And so the network is also going to be computing a sequence of actual outputs. The network will be computing a sequence of Ys in response to a sequence of X's. And the sequence of Ys is going to be compared to the sequence of Ds, the sequence of desired outputs. And the actual error that you will compute is going to be between sequences of inputs and sequences of outputs. So again, you must keep in mind that this entire computation, if I just illustrate all of the computation performed by the network, if I unroll the computation, it looks like one giant MLP. It is in fact just one giant MLP with lots of sharing. Every column has exactly the same parameters as every other column. And so network parameters can be trained via gradient descent using shared parameter gradient descent rules. And gradient computation requires a forward pass, as always, and a backward pass for computing the derivatives. Now, what does the forward pass look like? You're going to give it a regular input. You're going to give it the input. And starting from the beginning, you're going to compute your outputs through time. You can't just process all the inputs all at once, obviously. You have to start at the first time instant, and then you have to go through time. That's because when you perform your computation, you're going to first compute the hidden state over here, then the hidden state over here, and then the hidden state here. This hidden state cannot be computed without first computing the hidden states of the previous times. So you're going to be doing a forward pass going forward through time. I have some pseudocode for it. And the hidden state itself could be many layers. And for back propagation, you're going to start off with derivatives at the very end, and you're going to be propagating them backwards through time, right? So just for purposes of illustration, I've changed the figure a little bit so that I don't have arrows going in from the side and from the bottom. I'm showing all the arrows going in from the bottom, just so that we can see that there's actually just one input. When I'm feeding inputs to this guy, I actually have something coming out from here and something coming in from here, and I'm going to concatenate the two. And I feed it into the green box. So the curved picture is just meant to make this explicit. And another very key factor to consider is that the divergence that we will compute is not going to be computed independently at each time. These are time series models. They are computing series of outputs. And the desired outputs are also series of outputs. And so the error that you will compute is going to be the sequence of outputs produced by the network and the sequence of outputs that you want the network to produce. So for example, if you are performing machine translation, the network is going to output a sequence of words. the desired output is going to be a sequence of words also. There's no guarantee that there's a one-to-one correspondence between what the network produced and what you want. So a machine translation network may produce a sequence of words which has a different length, or maybe completely off, and it's arbitrarily long, and the output that you actually want is finite in length and well defined. So you are left with this problem of computing a divergence function where the inputs and outputs don't follow the usual format that we've always thought of when we are speaking of MLPs, where corresponding to each output is an input. Corresponding to each output is a desired output. Here, you actually have a sequence of outputs, an output sequence, and a desired output sequence, and there may really be no one-to-one correspondence between the two. Nonetheless, the two are not the same. So there is an error. And we need to be able to compute this error, and we need to be able to compute the derivative of this error with respect to the outputs of the network at each time. That makes sense, right? And so this error is not necessarily just a sum of the divergences at individual times, unless we explicitly define it as such. And that tends to be the biggest challenge with recurrent neural networks. When you have ugly error functions where you cannot find a distinct one-to-one correspondence between the output of the network and the desired output of the network, how do you compute this error? And how do you compute derivatives of this error with respect to the outputs of the network at each time? So once we assume that challenge is handled, backpropagation is straightforward. Now, so here is the notation that I'm going to be using to explain backprop. Y of t is the output at time t. If I put a subscript I, it means that the y has many components, and that's the ith component. The z here in my model, I have only one. In my example, I have only one hidden layer in the network. Of course, in the real network, you can have any number of hidden layers, right? So z superscript 2 is the affine value that goes in just below to the output layer. H of t is the output of the hidden layer, and z superscript 1 is the affine value that goes into the hidden layer, and x is the input. Now, I also have the representations for weights. W superscript 2 is the set of weights going to the output layer. W superscript 1 is the set of current weights going to the hidden layer, and W superscript 1 is the matrix of recurrent weights going across the horizontal edges. Now, what is the backprop? What does backprop look like? Now, regardless of how we define the divergence, we are going to assume that it's possible for us to compute the derivative of the divergence with respect to the output of the network, each of the outputs of the network. Because if you cannot compute that, then you can't really perform backprop. So a lot of what we will see in future lectures in the next couple of weeks is how do we compute the derivative of this divergence with respect to the individual outputs of the network when there's no clear one-to-one correspondence between the actual and desired outputs of the network. But assuming that that problem is solved, then you're going to, and of course, the problem is solved if you're performing simple problems like predicting stock, because you're going to have a stock prediction on every day, and you're going to have a true value for the stock on every day. So your overall loss is simply going to be the sum of the losses at each time, and then you can indeed compute the derivative of the overall divergence with respect to the output at each time. But that's just one special case. And so you have a divergence which is a function of all outputs, and we need to be able to compute the derivative of the divergence with respect to each of these outputs. And assuming that is that is possible, then there are two very simple rules that we are going to use when we perform backprop. And they're shown on the slide, but let's just draw them, right? Now, first, if I have a y I minus 1, which gives me a zi, which gives me a yi, and this is some function f, and this is some weight matrix, and the yi influences my loss, then what is the derivative of the loss with respect to z? The derivative of the loss with respect to z is going to be the derivative of the loss with respect to y over here, right, times the derivative of y with respect to z. Straightforward, right? We've done this many times. So, and that's going to be just the Jacobian. Now, what is the derivative of the loss with respect to yi minus 1? That's going to be the derivative of the loss with respect to zi, this guy, times the derivative of zi with respect to yi minus 1. What was this guy? That was just w. I can just write w, right? So we've written the second one. And what was the derivative of the loss with respect to w over here?
Derivative of loss with respect to z times y.
Is it what? The shape wise, it was actually the other way, right? So 3 simple rules. We've seen this many times in the past. That's one. And the second is if I have a single yi, which is influencing two z's, right? Then over here, the derivative of the loss with respect to y is going to be the derivative of the loss with respect to z1 times w1 plus the derivative of the loss with respect to z2 times w2, right? Because the loss is going to flow backward. The derivatives of the loss are going to flow backwards through both arrows. So once we know these 2 rules, then the gradient descent rules are very straightforward. Questions? Okay. So I'm going to start off at the very end, at the final time. At the final time, I'm going to assume that I am able to compute the derivative of the divergence with respect to the final output y. So when I'm propagating the error backwards, what would be the next derivative I'd compute? I'd be propagating that derivative down here and be computing the derivative with respect to the affine value at the final output, right? And for that, I'm just going to be using this rule that we just came up with. And so that's going to give me the derivative of the divergence with respect to the affine value is going to be the derivative of the divergence with respect to y times the Jacobian, right? So what is the next term I would compute if I were computing the derivatives propagating back? Anyone?
The derivative of y over d.
So that's going to be the derivative of the loss with respect to this guy, right? And so the derivative of the loss with respect to that h is going to be the derivative of the loss with respect to z times w. Straightforward. And at the same time, I can also compute the derivative of the loss with respect to w, which is going to be this h times the derivative of the loss with respect to the z. That's this formula that we're using, right? Nothing fancy. Again, we're not doing anything particularly complex. And the specific formulae are not relevant, not so important because you'll be able to figure them out on your own. But I'm just showing you the flow of derivatives that happens, okay? Now, once you're done with this, you're going to go down and compute the derivative with respect to this z, which is simply going to be the derivative with respect to h, or the loss with respect to h times the Jacobian of the hidden activation, which is what we have here. Again, nothing fancy. And then I can go further down and compute the derivative of the loss with respect to W1, which is the hidden state, which is the weight matrix for the hidden state, which is simply going to be the input times the derivative of the loss with respect to h, with respect to z1, right? So again, this is also fine. Now, which derivative would I compute next? Anyone?
yt minus 1.
I need to compute the derivative for this connection, right? Going back. And that is simply going to be ht minus 1 times the derivative of the loss with respect to z1 at t. Everyone with me? Right. And so I've computed the derivatives for the final time. And then I take a step back. And then I'm going to travel down the next column. And so I'm going to start here. And of course, when I start from the top, the first thing I would compute is the derivative of the loss with respect to the affine term at the second, at t minus 1. And then again, I can also, and now a couple of strange rules kick in. First, when I compute the derivative with respect to the output of the hidden layer at time t minus 1, there's a branching, right? And so I'm going to be using this rule. Because the hidden state had two branches, one going up, one going right. And so I correspondingly will have two components, the derivative of the loss with respect to this value times this weight, plus the derivative of the loss with respect to this value times this weight. Everyone with me? Right, okay, so this was easy. And then there's another thing. Now, this took into account the fact that there's branching at that point. But now when I begin computing the derivative of the loss with respect to the weight over here for this connection, what would I need to consider? Anyone? You have to take into fact that those weights are the same as the weights at the next time, right? These are shared parameter networks. And so when I go back, I would find that the derivative of the loss for this weight is going to be actually, you're going to aggregate the derivative coming down at the current time with what you already had. Because this edge and this edge had exactly the same set of weights. And so you say the derivative of the divergence with respect to W plus equals, because you have already computed some value at the next time, the derivative that you got for the weight over here at this time, which is the h times the derivative of the loss with respect to the z here, right? So again, observe how the derivatives got accumulated because these are shared parameters. And then I can just continue as before. I can propagate the loss derivative down through the activation to the affine value below the activation. And then I can propagate the loss derivative to compute the derivative for this weight, right? And the derivative for this weight over here is again going to be, since this weight is the same as this weight, I'm going to have a plus equals, which means that the derivative that I want to compute for this W1 is going to be the sum of the derivative I got over here plus the derivative I get here, which is xt minus 1 times the derivative of the loss with respect to the z, right? And so you can see how as you keep going backwards, these derivatives will continue to get accumulated. And then so also, if I'm looking at the recurrent connection, this guy, this derivative will also get accumulated in the sense that you already had a derivative that you computed down this connection. That is going to be added to the derivative that you have here, right? So that's a plus equals, yes.
Also, does that mean that there is more like importance or priority to the first layer than to the last layer because the weights are just getting accumulated or added up? Can we take an inference?
So the point is, it's not, this is the derivative with respect to the weight and not the weight at that position, right? Eventually, you're just going to have This is like saying I'm computing a derivative at each of these connections and then summing them all up. There's no additional importance being assigned to any given time. Right? Yeah.
It seems to me like you almost be like over counting or like.
You're not overcounting. So the way to think about it is I'm going backwards. Remember that these derivatives are not being propagated, right? These are just the derivatives with respect to parameters. So when you get all the way to the beginning, you're going to have a bunch of derivatives with respect to the w's. Alternately stated, you can just say that I'm going backwards, I'm computing derivatives with respect to all of these weights, and then I'm summing them, every single column, and then summing them up. So there's no overcounting, right? Yeah. Was there any other connect? Okay. And you can just continue this process all the way to the beginning of time. So it's all fairly straightforward. The only distinction between this and a regular MLP is that now you have recurrence. And so recurrence really means that now you have parameter sharing across time. You have to start off gradient computations at the final time and work your way backwards. And also at any point where you have a branching with information with values both going up and to the side, when you have derivatives coming back, you're going to be summing derivatives across all output branches, right? So, and of course, for the parameters, you're going to be accumulating derivatives across time. And so we have some pseudocode for the whole thing. Any questions? Yeah.
Can you explain the part about it being a shared parameter network?
It's a shared parameter network because every column is identical to every other column, right? At time t, you're using the same network to make the prediction at time t as you're using to make the prediction at time t plus 1.
So each of the weights for each column are identical?
No, what this means is that this weight here is the same as this weight here, right? So also this weight here is the same as this weight here. It doesn't mean that this weight is the same as this weight. These are two different weights, right?
So they're identical units?
They are identical across time, not across the columns. So every copy of the same arrow has the same weight. So for example, the weight for this connection is the same as the weight for this connection is the same as the weight for this connection, because you're basically just repeating the network across time. But if I saw the entire computation as one giant block, it looks like a shared parameter network.
So when we backpropagate, we just add the derivative to the derivative of the same shared parameter.
So for example, yeah, if you wanted to compute the derivatives of the loss with respect to, say, W11, then you're going to get the derivative of the loss with respect to W11 here, a separate derivative here, and so on. And all of those are just going to be summed up, right? That's, yeah.
Assuming the data set allows for it, the time step is also a hyperparameter for a network like this, right?
Meaning you're assuming that it's just that each input is the next, that it's a sequence where, the only thing that matters is the indices.
Okay.
Now you could have stuff missing in between, which means that there are time instances where you have no inputs, but that's it.
Okay.
Right? So that's like saying x is 0 at that time.
It seems like this process is going to be slow because both the forward and the backward are very sequential.
It is going to be slow. There's no parallelism possible, right? That is a problem. That's why we don't actually use these structures anymore. We use transformers, right? But again, they're very powerful. The big issue is the sequentiality. So to give you an idea of how this works, to answer your question, here's the pseudocode for how I could actually be computing my derivatives, right? I have my derivatives going down the output layer at any time. I'm going backwards through time. Then when I'm going backwards through time, I start off with computing the derivatives for the output layer. Then I go backwards through the layers. And real aggregation happens over here, which is that when I compute the derivatives for the current or the recurrent weights, I'm just always accumulating them all the time when I'm going backwards through time, let's say. Now, and this, of course, can be generalized to pretty much any architecture. The same idea holds, right? So. Okay. First statement, is it true or false?
False.
How many of you think it's false? Good. Okay. And what about the second one? Is the first, and the second question, is the first statement true or false? So the divergence we minimize is the sum of the divergences at the individual time. Is this true or false? False. We said that there's no, that would just be a special case, right? The real divergence you're computing is the divergence between sequences, and we have no idea what that really looks like. We're just kind of hoping that you can decompose it as the sum of divergences at individual times. And the divergence is the divergence between the actual sequence of outputs and the actual sequence of desired outputs. So the second statement in the second question, true or false? True, right? Okay. So these are the true statements. Now, and there are various extensions to the basic idea. But the most interesting one is that once you begin introducing recurrence, then you can actually have two different kinds of recurrences. You can have recurrences going forward, and then you can have recurrences. Can you guys shut your laptops? Yes, thank you, right? So, unless you're taking notes. Okay? Unless you're taking notes. Okay. So if you can make inferences going forward, you can make inferences going backwards. So just as in a time series, what happens now influences the future. If I look at what happens in the future, it tells me something about what has happened now, right? Or if I think of something like in language, if I want to do some kind of a part of speech tag, the previous words tell me whether the current word was supposed to be a noun or a verb. But so do the future words, right? And so just as you can have recurrence going forward, you can have recurrence going backward, and you really want you want evidence both from the past and from the future. But if you want to have evidence from both the past and the future, you would need, this is going to have your forward recurrence, right? Where the past influences the future. But if you want to look at the future, and in many cases where I'm giving you a complete sentence and I'm asking you, what is this word? Is this a noun or a verb? Then the information about whether it's a noun or a verb is not only in the past but also in future words, and you already have the future words. The input is not coming in streaming. The entire input is being given to you, right? So in that case, you might want also to look at information from the future in order to be making the inference at any time. But then what is the problem with this kind of a structure? When I have, like the one I've shown on the board, what would be the problem?
You need to train the future time step to train the previous time step. And
forget about training, even during computation, right? So when I'm performing my computation, this is used to compute this guy. But then this is used to compute this guy. So I have a loop. There's no way for me to actually stop computing, right? And that's a problem. So there's this beautiful paper by Paliwal and Chester where they showed how you can deal with this. And the way you deal with it is not by having a single network which has both forward and backward connections. You separate it out. You have a forward recurrence which is distinct from the backward recurrence. I'm going to go over by a couple of minutes, guys. Just bear with me. So here's what the network looks like. Within each layer, you have one portion of the network which starts at the beginning and performs a recurrent computation to the end of the end. And you have another layer which starts at the end and performs recurrent connections going back to the beginning. And both of their outputs are now concatenated or somehow combined to give you the final output at each time. So if you look at the final output, it's typically a concatenation of HF, which is the outcome of the forward recurrence, and HB, which is the outcome of the backward recurrence, right? So, and so how does the actual computation operate? You would have the forward net, which is going to perform your forward recurrence. You have your backward net, which is going to perform your backward recurrence. And both of their outputs are finally concatenated to give you the final output at each time. Now, you might imagine that this causes some kind of issues when you're performing back propagation, but it really doesn't. Nothing has changed. So what would happen here is straightforward. Let's say I have a 10-dimensional input which goes in, and then I have my forward network which computes a 10-dimensional input, and then I have an output, and I have a let's say this is 5, right? And then I have a backward network which also computes a 5-dimensional output, and these two guys are concatenated to give me a 10-dimensional output for the entire block, right? When you're computing your derivatives backwards, the derivative of the loss would have 10 components out here. You take the first 5 components and get a 5-component derivative here. You take the next 5 components, you would have a 5-component derivative here. These can be passed in, and coming down each of these lines, you'd get a 10-component derivative. The derivatives would just get added up. So the backprop rules end up being fairly straightforward with no particular complication. Now, again, so the bidirectional block itself can be used in any odd manner, right? Within the bidirectional block, you can have many of these bidirectional blocks, or you can even alternate them with unidirectional blocks. And within each bidirectional block, the forward and backward networks can be arbitrarily complicated. Doesn't really matter. The key point is the backprop. We have a final poll, then I'll spend a minute on backprop, and then we'll let you go. True or false? Who said false? Why?
I think he may be wrong, but I think he will know the future.
So a trader will not know the future. They cannot use a bidirectional network, right? You need to have, in order to use a bidirectional network, you need a problem where the entire input is provided all at once. So you can see both the past and the future. And I have some code for it. Now, the magic thing about the bidirectional network is that the forward recurrence and the backward recurrence are basically the same code. You can just pass the input flipped in time and the corresponding set of parameters to the same code, right? And so in the forward pass, you'll be computing both the forward and backward portions of the recursions. And then when you're computing backprop, at the output of the block, you expect to see the derivative of the divergence with respect to the hidden values at each time. So you'd see the derivative of the divergence with respect to each HT. And that derivative is going to have 2 components. The first half is going to be the derivatives that you got that are for the values that you got from the forward portion of the network, and the second half is going to be the derivatives for the values that you got from the backward portion of the network. And so you could just use these guys, the first half of the derivatives that you got with respect to h for back propagating through the forward portion, and this portion, the second half, which is the derivatives that you got for the second for the outputs from the backward portion of the network to perform back prop for the backward recursion. So for this guy, you'd just be using the derivatives with respect to hf, and you'd be performing back propagation going backwards from the end to the beginning. Whereas for the backward recursion, because the actual computation started at the end and went back through time, although I'm calling it back prop, it's going to start from the beginning and go forward through time, right? And there you're just going to be using the derivatives for HB that's going to go forward, right? And now when you further propagate the derivatives downwards through the forward and the backward networks, you're going to have, again, observe that this value is getting branched. One branch is going into the backward portion of the network. The other value is going to go into the forward portion of the network using the same branching rules. The derivatives that come down this line and the derivatives that come down this line are simply going to get summed up to give you the derivatives with respect to the input. So again, the actual back propagation rules are very straightforward, simple, right? Nothing complicated. And the coolest thing is that when it comes to code, it's not very complex because the backward recursion is basically the same as the forward recursion with the input reversed. So I have pseudocode for it. And so to close out, what we finally added in the last few minutes of the lecture was that bidirectional networks analyze data both ways, beginning to end and the end to the beginning. In these networks, the backprop rules must follow the chain of recursion and gradient pooling separately for the forward and backward recursion. And then when you go down out of the block, the gradients must be aggregated. So I'll stop here, and we'll pick up in the next class. I'm still not sure if I'm going to have a class on Friday or not. So please bear with me. I'll make a post about it later today, depending on how things are. And we may just have, if we do have a class on Friday, it will be at this time. Right? Thank you, everybody.